Imagine there is a ground, and on it we have a circular platform like a turntable or like a merry-go-round. We know that the ground around the platform does not move, but the circular platform can rotate. Let us now introduce a coordinate system. Let the center of the platform become the origin of our coordinate system. First, we consider a set of axes that never move. These axes are painted on the ground. One axis points to the east and is called XF. The other axis points to the north and is called YF. These axes always stay fixed in the same direction no matter how the platform turns. Because they never move, we call them the fixed frame. Now we place another pair of axes directly on the platform itself. These axes also start from the same origin or the center of the platform. One axis is called XM, and the other is called YM. The important thing is that these axes are painted on the platform. So whenever the platform rotates, these axes rotate along with it. Because they rotate together with the platform, we call them the moving or rotating frame. At the beginning, imagine the platform has not rotated yet. In that situation, the moving axes XM and YM lie exactly on top of the fixed axes XF and YF. So both frames are perfectly aligned. Now imagine there is a small ball glued on the surface of the platform. This means that the ball moves together with the platform. So here is the situation we are interested in. We know the coordinates of the ball measured using the moving frame XM and YM. These numbers stay constant because the ball moves together with the platform. Our goal is to calculate what the coordinates of the same ball are in the fixed frame XF and YF. To answer this question, we will introduce rotation matrices into the picture. Our goal is simple. Suppose F represents the position of the ball measured in the fixed frame, and M represents the position of the ball measured in the moving frame. Then we want an equation which can describe F in terms of M and the angle theta through which the merry-go-round has rotated. This rule will turn out to be multiplication by a small 2x2 matrix R, and that matrix is called the rotation matrix. So, spoiler alert, finally we will get F equals R times M. Let us see how. If the coordinates of the ball are XM and YM in the M frame, then this will be XM and this will be YM, right? Also XF and YF will be this. Okay, now it's trigonometry time. Look at this right triangle. If this is XM and this is angle theta, then the horizontal contribution from the XM is XM multiplied by cosine theta, and the vertical contribution is XM sine theta. Now look at this right triangle. If this is theta, then this will be 90 minus theta. So this will also be 90 minus theta, and therefore this will be equal to angle theta. So if this is YM and this is angle theta, then the horizontal contribution from the YM is YM multiplied by sine theta, and the vertical contribution is YM cosine theta. Now this distance is XF, or the horizontal coordinate of the ball in the fixed frame. So we have XF plus YM sine theta equals XM cosine theta. This gives XF equals XM cosine theta minus YM sine theta. Then this distance is YF, or the vertical coordinate of the ball in the fixed frame. So we have YF equals XM sine theta plus YM cosine theta. Noise. The next step is simply to organize these two equations in a cleaner way. Instead of writing them separately, we can combine them into a compact matrix form. We can rewrite this as a column vector XF and YF. Then this as some 2 cross 2 matrix multiplied by another column vector XM and YM. What will be this matrix? It will contain this cosine theta, then this minus sine theta, then this sine theta, and again this cosine theta, And folks, this is what we call the rotation matrix R. So we have written F equals R times M, where R is this rotation matrix that converts coordinates from the moving frame into coordinates in the fixed frame. That is simply mind-blowing. Now, since this rotation matrix is an orthogonal matrix, therefore its inverse will be the same as the transpose of this matrix or this. So only the minus sign will come here. So this means if we are given the coordinates of F frame and we want the coordinates in M frame, then we can simply do M equals R inverse times F. See how easy that is? Now let us look at a nice example. Suppose we have an ellipse in a moving frame described by the equation xm squared over 3 plus ym squared over 2 equals 1. Now imagine that the moving frame has rotated counterclockwise by 45 degrees relative to the fixed frame. Our goal is to find the equation of the same ellipse in the fixed frame xf, yf. This means we have to find m in terms of f and substitute it here. This is now very simple. The rotation angle is 45 degrees. For 45 degrees, both cosine and sine 45 degrees equals 1 divided by square root 2. So the rotation matrix R will be this. Therefore, its inverse will be this. Now multiply it with xf and yf vector to get this. So xm equals xf plus yf over root 2 and ym equals yf minus xf over root 2. Now we substitute these expressions into the equation of the ellipse. Expand them. This becomes xf plus yf whole squared divided by 6 plus yf minus xf whole squared divided by 4 equals 1. So this is the equation of the same ellipse expressed in the fixed frame. That was super cool! If you enjoyed this video, please don't forget to like, share, and subscribe to our channel. Also, you can support my channel by joining our community and becoming a member.